Hey everybody, this is going to be a tutorial on Synopsys TCAD. I won't be going over exact syntax. Instead, I just want to go over the general concept of how each code block and tool works. Now, you're not going to have server access by default, and in order to get in, you first need to email ASUIT, and then you're going to need two programs. The first is called PuTTY. Once you get access, you'll be provided the server information, which I'm entering here, and then you can enter in the same login that you use to get into My ASU. Alright, now really you only use this window for two things. The first is this VNC server command. What this does is give you an address to log in with. The last time I logged in it was 2, now it's 3, which means that at this time of the day more people are getting on. And as more people start using the server, the slower it gets. Once we have the address from PuTTY, we can go ahead and download and enter it into VNC Viewer. Using the same login information, we'll start up a virtual machine session. The reason being is because all of the licenses and probably all of the computing power to run all of these simulations are housed on ASU's Linux server, so that means none of this can be run locally. Now, you'll need to have the basic skills on how to use Linux, like how to do basic command line. For example, if something is stalled, you type in table of processes in this terminal. But anyway, the first thing we want to do is make sure we have a specific folder to store all of our projects in. Go ahead and put something in Documents, and you'll notice that inside my dedicated folder there are individual folders for each project that we've opened up. If I open up this one, for example, you'll see all of these node numbers which correspond to individual experiments that we've run, but also we'll see these .par files. I want to say this at the outset, you shouldn't need these in the root folder, but if you ever get an error saying that there isn't a recognized material or that a material property is missing, it's helpful to navigate into the system files and then bring over these parameter files into the root of your project. Once you have your folder set up, you can go to the terminal, and each individual element of the Centaurus software package has its own identifier. So SDE would be the device editor, but really we want Centaurus Workbench because that's how you can access everything else. Alright, now before I go into our group's simulations, I wanted to show off all of these example files. The reason they matter is not only do they tell you roughly how to run something and whether your system is capable of it, you can also see the types of tools and approaches that are used. So for example, if you see something running in an example file, you can go ahead and basically steal it. Very often you'll look in the manual that's available and something won't quite work, or maybe something won't be very clear. You can use all of these example files as a base. However, if you want to make changes either to the input files or to these variables, you're going to realize that they cannot be changed. You're going to need to find the system path for these files and then copy them into your own document in order to make those changes. Alright, now let's go ahead and go to one of our group's devices. In that last example program, you saw something called S-Process. You're not going to need it because that simulates the manufacturing process used to make the device. That's if you want to simulate imperfections, but that's beyond the scope of our own project. Instead, we use two different tools. One is called SDE and Sdevice. In order to start these, you're going to make a new project, and I'd suggest a traditional project. The difference between these two is how the output files are stored. Then what you can do is you can add a tool, either by right-clicking this toolbar and hitting Add, and then you're going to have a menu. I'm hesitant to click this just because it can take a while. And then you can add one of these. Be forewarned, if you add in a tool, it will show up on the right side of whatever tool you're using. And what it can end up doing is sliding along all your variables. For example, you make another tool, and then under that tool, all these variables are going to show up. The reason this matters is that when you go into this command file, you're going to see all these @ symbols up top. You don't want to hard code everything. You want to make as much of your system automated so that you can change things on the fly. So for example, if we look to @pillar width, we can see pillar width right here. And if I right click here, I can add more values. For example, I could add 2 and it would show up in the list. And it would double everything. So there would be twice as many nodes because there are twice as many combinations. This is how this works. In both SDE and Sdevice, you can make another variable name and then put values under it, and then reference those variables inside your input files. However, it may seem daunting to code a device structure just purely based on a command line interface. This is why we use a bit of a combined approach. You can see right here all of the different components of the Synopsys package, and we're going to go ahead and open up Structure Editor. Now, if I want to do something simple, like just make a rectangle in silicon, I just select this tool and do this. And then I would go on to build up the rest of the device. If there were major material changes, like one side is silicon carbide 4H and then the next rectangle is aluminum, I would change the material here. You'll notice here that these scheme commands are being saved, or rather they would be saved if I typed in journal and then turned on the journal on. The reason we want to save these commands is that this model is pretty useless in and of itself. We need to have the text version of this whole thing in order to enter it into SDE. So let's go ahead and hit no here, and I'll show you what that roughly looks like. So if I go to VDMOS and I go to SDE and I hit run, it'll probably take just a few seconds to build up this whole thing. And we can see here we have all of these rectangles. This is what I mean. There's no point building it up and then trying to integrate it into your flow when you can just have all of these text files. Now you'll see a passage in here that says meshing successful. For that, I'm going to need to explain what each block in SDE does. I'm going to go ahead and close this, or rather move it out of the way, because we don't need to see what's going on each time. Sorry about that, that's the wrong one. So most of the time under each tool you can go to Edit Input and Commands. This applies to both Sdevice and SDE. When we move to the top here, we first see these define macros. Anything that you want to reference should be put up here, and that means anytime you use the word p-width, it will, as it compiles, it will replace it with whatever you have here, which is whatever you have here in this little Excel chart. Then, all the rectangles that you made in the graphical editor should be saved here, whether they be, say, silicon carbide 4H or aluminum. Once you've made all these rectangles, and there's really no easy way, you either have to make your own structure or go to the literature and then laboriously copy down what you think the values should be. Once that's done, you need to dope the device. So in order to dope the device, you need to, if you want to create a shortcut, in order to not have to specify it every time, it's recommended to essentially use this syntax here to set up your negative and your positive dope it. And then, once you have all of these set up, you can simply copy them over again. Replace is kind of funny. All this means is that all of your predefined regions that you did in the graphical editor, you're going through them and applying these values. And for example, P plus here, that is the value of the doping that you would apply to that region. The next thing you want to do is set your contacts, and you need to do this twice. The first time, you call it source, gain, and drain here. And you really need only a point on an edge. This find function will find and select the whole edge. And you also need to do it twice. You go here in Sdevice, and you need to make sure that the contacts for source, gain, and drain, for example, are named the same as they are in your SDE file. Otherwise, it'll fail. The last thing you need to do is meshing. We're not referencing the region names anymore. We're just going along and seeing where we want more resolution. You'll notice here, for example, high and medium mesh. The reason we care about how much something is meshed, we can actually see it right here. If I click here, where all of these define ref eval windows are in place, you'll see the result. And just as an aside, anything that has a .tdr suffix cannot be opened in the Node Explorer. It has to be opened separately in this visual interface. You can see right here that there's like a harsh line where there's some amount of meshing, and then there's a very fine degree of meshing. We can see the difference between this level of meshing and when we comment out all of these ref eval windows. So I'm going to go ahead here and open it a second time. This right here represents meshing. By default, it's turned off, and then when we turn it on, we can see what it is. And as you can see, there's barely any resolution here. It's just a couple triangles per region. This is how it's going to be by default, and it's going to be absolutely worthless in terms of making good results. However, you should not start meshing right away. You should instead make your structure, then run your electrical simulation, see where there is insufficient resolution, and then set more meshing. One last thing I wanted to mention, I said commenting out. This is going to be different. If I open up Sdevice here and edit the command file, you're going to see these hash symbols. The reason is that this is in Tickle, while the structure editor is in Scheme. They're two different scripting languages. That's why whenever we want to comment something out here, we terminate with a semicolon, and then everything afterward is not read in the line. It's just two different ways. Thankfully, the way to use variables, this @ symbol, is the same across both languages. Alright, now that we have understood SDE and how to make our structure, we need to understand how to run experiments on it. I'm not going to be looking at ion strikes right now. I just want to show how to run an electrical simulation. Now, this is going to be very complicated. You're going to have models. You're going to have what you want it to output. You're going to have the solver properties, and then the specific simulations you want to run, including plots you want to make. Let's start with the models. You'll notice here that this, and I'm talking right here, this section right here, there is a section here called Avalanche Akudo. And yet, when I go to this vertical structure, and I open its Sdevice file, there is no such section. It's hard to believe, but just adding in one keyword with the name of a model as specified in the manual can completely change the scope and time of your simulation. You could add this and it could explode from a couple minutes to a few hours. And this is important. For example, if I look at the IV curve, which is something important that you're going to want to do, and I open this up, I did open it 3 times, which we should not do. You shouldn't do what I just did. Okay, let's make sure that's the only window like that. All right, so IdVg. So we go to drain current, set it as X, and then gate voltage, set it as Y. you'll see this very typical IV curve, but you won't see is breakdown, which is when this thing starts to tail up and then rapidly shoot upwards. This would indicate device breakdown. The reason I mention this is because we have an insufficient amount of models. As I explained, right here we don't have that avalanche simulation, while in this we did have avalanche simulation. Now these are different structures, but I'm just generally explaining the concept that if you don't have the correct models selected and simulated, your simulation results can be dubious. And there's really only one way to do that is to do trial and error. What you do is you find an example file and then you start adding in the different models one by one and see which ones drastically change the results. All right, so now that we have this file stuff is boilerplate, you'll see it in all the example files. Now that we have the models specified, I'm going to go ahead and skip over this heavy ion section. This you don't need to worry too much about. You just copy it from one of the example files. The reason is that everything that is specified here will be plotted in a 2D fashion. To illustrate this, let me go ahead and open up one of these simulations. That's wrong. I'm going to go ahead and open up the result of what I think is a 100-volt simulation. Inside, we're going to see the likes of current density, impact ionization, and for some reason it's not loading. Let me go ahead and, yeah, there we go. So here we have this whole list, and remember this icon last time? This shows us the meshing that is used for each individual. All right, so let's go ahead and look at something like electric field in both directions. For example, you'll see a buildup at the bottom of these pillars. That's probably not going to apply to your structure, but that's something that you would notice right away. You can see, unfortunately, lattice temperature isn't really working here. As you can see, everything is blue here. But this would be really helpful to find out when the device burns out. Now, for our purposes, we click here on impact ionization, and you'll see that one side is not like the other. That's because in addition to doing an electrical simulation, we also did a heavy ion simulation. So this is what it looks like with just electrical activity, and this is what it looks like with the heavy ion. We can see what happens when we go here. We can see that I specified an ion track here, and resulting heavy ion generation happened here at the top portion of the pillar. So now I need to explain how both electrical and heavy ion simulations work, and for that we go back to the command file. So in this solve section, if ever you get something where it says Newton didn't converge, the smart thing to do would be to go here and fiddle around with these solver properties. But the dumb thing, and the thing I always end up doing, is just to increase or rather decrease the min step. It'll make your simulation take hours, but it will usually make your simulation converge. Now, you'll see these quasi-stationary and these transient simulations. You do not need this transient simulation if you are doing an ion strike. However, once you've set up this quasi-stationary simulation, which you can just copy, and you'll notice here that you are moving the device toward a certain drain voltage. Up here, you may have been tempted to set a voltage for your electrodes, but that is bad. Maybe it'll work at very low voltages, but at high voltages, your simulation will not converge. Instead, you need to gradually turn on the device with this quasi-stationary simulation, and then at the end, you will have an electrical simulation. However, if you were doing a heavy ion strike, you should do another simulation in which you hit it with a heavy ion. In order to, now you can just copy the syntax here, and the timing is relevant here. Whenever you hit the simulation, or rather hit the device with an ion, should be matched with this final time. You'll see this heavy ion section here, Before I explain this little code block, I want to explain material properties. So if I go here to edit inputs, before you ever created this Sdevice tool, you also want to put in all of your materials, which is these .par files that I mentioned. However, as we move over into these later device sections, they also have a heavy ion section. Okay, should be in this last one. All right, I'll have it in the description, but basically there's an equation that governs how the heavy ion moves through the device with 4 terms, and some of these are either set to 0 or 1. The other setting that you will need to change is the heavy ion itself. So you need to put the heavy ion in the parameter file, but you also have to have the parameters of the specific ion strike. LET is going to be governed by the element hitting the device as well as the device material. In our case, it's lead and silicon carbide 4H polymorph. We also put the time that it happens as well as where it happens. In 2 different devices, I have the start point happening in 2 different places, so I either hit the gate or the pillar. And here you'll notice that this is half a picosecond, while our full simulation time down here was a full picosecond. So this thing is being hit halfway through the transient simulation. This is just the width, and you should just experiment to see what gives you the most meaningful looking results, and length should not exceed more than half of the length of your device. Alright, so let's say you have managed to get your SDE working, you've gotten your Sdevice working. What do? Well, the answer is that you start fiddling around with these values. You shouldn't fiddle around with your device simulation until you've gotten satisfactory electrical simulations. And in order to do that, you really need to go through the voltage range. So you start at 100 going to as far as it'll go. I'll tell you right now, once you start hitting a certain voltage range, the simulations will go to 24 hours. And that means the server will reset itself and terminate your simulation. In my experience, this happens at around 6 or 7 a.m. So it's good to start a simulation in the morning, maybe at 8 or 9 a.m. after this happens, so you have the most time in order to get this simulation running. That's really it. To recap, you log in, you create a new project, you create SDE and Sdevice tools, you create your structure, you automate the structure changing using these variables, you automate the Sdevice changing using these variables. So long as you have the right parameter files and the right command file structure, you should be fine. The last thing I want to mention is plots. At the beginning, I talked about an IdVg curve. I'm going to go back here and just show you the syntax of that. There are 2 commands you need to be familiar with: new current prefix and current plot. So you'll see this right here, new current prefix IdVg, which you do at the beginning right before a quasi-stationary statement, and then inside the quasi-stationary statement after the coupled statement, which tells us what it wants to solve for, you do this. Range and intervals. This matters because quasi-stationary goes from 0 to 1 in terms of time, and intervals 10 just means that you are setting that many equidistant points, so you don't overwhelm your hard drive with an point every single iteration of the simulation. That should be everything. If you have any questions, go ahead and send me an email. This took us months to learn, and so hopefully all of this saves you a lot of time in working with this software.